Today we're going to talk about how to take the inverse of a function. What does that mean geometrically, like looking at a graph to take the inverse of a function, and algebraically, how do we find the inverse of a function? Well, before we can do that, we have to go back to our definition of a relation. Hopefully you remember what a relation is. It is a mapping of input values onto output values. So if you look at this example here, let's say I give you a table of values. This is your input, your x, your domain values. This is your output. So I'm doing some rule to my input values x to get my output values y. Well, what the inverse relation is and does is it maps the output values back to their original input values. So if I'm looking at the inverse relation of this original relation, you should notice that the input values are your output values for the inverse, and your output values of your original relation are the input values of your inverse. So that means the domain of the inverse relation is the range of the original relation, and the range of your inverse relation is the domain of the original relation. So we've just kind of interchanged the x and the y values. Now, what is the graph of an inverse relation look like? Graph of the inverse relation. Well, if you were to plot these original points, you'd get one graph, and once you interchange the x and the y values and you plot those corresponding points, what you will notice is that you get the reflection of the original. So the inverse is a reflection of the original relation across the line y equal x. So this is very fascinating, and we'll have to do the activity together. I wanted you to do a discovery activity to discover what it is graphically, but we can do that later since I'm not there. So algebraically, what is the definition of an inverse of a function? So the definition, if f and g are two functions, such that if we take the composition f composed with g, and we take the composition g composed with f, so we're taking the composition in both directions, that both of those will equal x for every x in the domain of G and in the domain of F. So that is how you would verify that two functions are inverses of each other. Two functions are inverses of each other if and only if taking the composition in both directions give you the same thing, and the same thing that you get is x. So how do we represent taking the inverse of a function? Well, if you have the function g and it is the inverse of the function f, you represent that as f with a superscript of -1. And you read that as f inverse. So this notation here is just read as f inverse. So you're taking the inverse of f. So f composed with itself, and this is missing a little close parentheses, f composed with its inverse is x, and f inverse composed with f is x. So the domain of f is equal to the range of f inverse and vice versa. So hopefully you're recognizing that. So as we just said, to verify functions are inverses of each other, you have to take the composition in both directions. So you'd have to take f of g of x and g of f of x, and you would need to show that they both equal x. So let's go ahead and do that. You have two functions. You have f of x and you have g of x. So I'm going to compute the composition of those two functions in both order. So remember, you work from the outside in. So I'm going to begin with f of x, since f is on the outside, which is 3x plus 2. And what am I going to substitute in for x in my outside function f? I'm going to substitute in g. So now I'm going to substitute in g for x. So I'm taking f of g of x, and that would be 3 times, we said x is g of x, and this is g of x, so that would be x minus 2 over 3 plus 2. So if I look at the right-hand side of that equation, I can simplify. And that is going to give me x minus 2 plus 2, which is just x. So I have shown that f composed with g, with respect to x, is in fact x. That's not enough to prove that the two are inverses of each other, because we still have to take the composition in the other direction. So now I'm going to start with my outside function, g of x. So if I start with g of x, which equals x minus 2 over 3, I'm now going to substitute in f of x for x. So that would be g of f of x equals f of x, which is 3x plus 2, minus 2 over 3, which is just 3x over 3, which simplifies to just x. So g of f of x also equals x. So since the composition taken in both directions of the two functions equal x, we have that they are actually inverses of each other. So graphically, we said that taking the inverse of a function is just reflecting it over the line y equal x. So if I have the line y equal x, then if I begin with a function and reflect it over y equal x, I have the inverse. So let's go ahead and take a look at that. If we were to graph f of x, we could graph it by plotting the y value of the y-intercept, plotting the y-intercept, and then rising and running the slope. That is one way we could do it. So the y-intercept would be 0, 2, and the slope would be up 3 over 1. However, I could also create a table of values. So I could choose x values, and I could substitute into f of x and get the corresponding y values. So if I substitute in these x values into f of x, again we see our y-intercept, I would get the following ordered pairs. And I could plot those points: -2, -4, -1, -1, so that actually falls on the line y equal x, and it'll be a very important point. 0, 2, 1, 5, 2, 8. So I could graph that line to the best of my ability, and that would be the graph of my function f of x. Now, knowing what we know about the relationship between the domain and the range of a function and the domain and the range of its inverse, if I were to take the function g of x, I know that the domain of f becomes the range of g, and the range of f becomes the domain of g. So we're interchanging the x and the y values. So I know for g of x, if I were to substitute in these values for x, so -4, -1, 2, 5, 8, if I were to substitute those in for x into g of x, I should get the domain values for my function f. So go ahead and try that, verify that, and you do. So that this point here, -2, -4, is being reflected over y equal x and giving me -4, -2 for my function g. Similarly, the point -1, -1 is already on the line y equal x, so it stays there. The point 0, 2 is reflected over y equal x and becomes 2, 0, for g. Similarly, we have 1, 5 on f becomes 5, 1 on g, and 2, 8 on f becomes 8, 2. So now I get the reflection of f of x over the line y equal x to get my inverse g. Now, one thing that you have to be very careful with is notation. So when you look at a function with a superscript -1, I do not want you to mistake this for a -1 exponent. So this is not the same thing as putting 1 over the function. That's nonsense. So when you see a function raised to that -1 superscript, that means the inverse of the function f. Now, algebraically, it's quite easy to find the inverse of a function. Knowing that the domain of a function becomes the range of its inverse, and the range of a function becomes the domain of its inverse, it makes sense that all you have to do is, given a function f of x equals 3x plus 2, first represent f of x as y. And then you want to interchange the x and the y in the original function. So in other words, this y becomes x, this x becomes y. So I'm just rewriting it, interchanging the x and the y. The next thing you want to do is just solve for y. So we are solving for y. So if I solve for y in this equation, I'm going to go ahead and subtract 2 from both sides, giving me x minus 2 equals 3y. And then I'm going to divide each term by 3. So that is going to give me y equals x minus 2 over 3, which we know, because we've worked this example quite a few times, is the inverse of x. Now, how can you check it? Well, again, to verify two functions are inverses of each other, all you have to do is take the composition in both orders. So f of f inverse should give us x, and f inverse of f, the composition in the other direction, should give us x. If that is the case, then you have in today's lesson. Now, if you recall, we could perform the vertical line test on a relation to determine if it is a function. Well, how are we going to determine if the inverse of a function is also a function? Well, we have what is known as the horizontal line test. This is beautiful. So if you can draw a horizontal line through a function, then its inverse is not a function. However, if no horizontal line intersects the graph of a function more than once, then the inverse of the function is also a function. So let's go ahead and use the horizontal line test to determine if a function has an inverse. Can you give an example of a function that does pass the horizontal line test? In other words, if you were to reflect the graph of that function, its reflection across y equal x would also be a function. Well, if you take the parent cubic function, which you should be familiar with, can you draw a vertical line and pass through it more than once? No, so it definitely is a function. It's the parent cubic function. But the question is can you draw a horizontal line through the graph anywhere and cross it more than once? No. So we know that the reflection across the line y equal x of f is going to be a function. And what is that going to look like? Well, it's going to look something like that. So how do we write the equation? Well, we just said algebraically we interchange y and x and we solve for y. So then that means I'm going to take the cube root of each side and I'm going to get y equals the cube root of x. So the inverse of f is the cube root of x. And it is a function. Now, can you think of a function that does not pass the horizontal line test and therefore does not have an inverse function? Y equals x squared, the parent quadratic equation. So we know what that graph looks like. And if I were to reflect it across the line y equal x, well, its graph would look like this. Now, we know that's not a function. So if I were to reflect f across y equal x, I'm going to get the graph g, which is not a function. And we could have seen that because the original function does not pass the horizontal line test. So it makes sense that the reflection across y equal x does not pass the vertical line test. And again, I could solve for the inverse by interchanging x and y and solving for y. So I'm going to get y equals plus or minus the square root of x. So in essence, the top part here in the first quadrant would be y equals the square root of x. This would be y equals negative square root of x, not a function. Now, if I can continue, I would like to introduce some very special functions. Very special functions are known as one-to-one functions. Now, one-to-one functions are functions that pass the horizontal line test as well as the vertical line tests. In other words, each output value, each y value, corresponds to exactly one input value. So, what does it mean to be one-to-one? Well, that means we have a function whose inverse reflection across y equal x is also a function. So we can use those same two examples as we did previously. For a function that is one-to-one, we can have y equals x cubed. Again, passes the vertical and the horizontal line test. And we can give an example of a function that's not one-to-one. In other words, a function that passes the vertical line test but not the horizontal line test. For a function to be one-to-one, it must pass the vertical and the horizontal line test. Now, can we find the inverse of a function and graph both the function and the inverse on the same Cartesian plane? Well, let's go back to our example, y equals x squared. Y equals x squared. Now, we said this wasn't one-to-one. If I were to graph y equals x squared, I'm going to get this graph. Now, it passes the vertical line test, so it is a function, but its inverse is not a function. However, we can restrict parts of this quadratic parent function, look at only pieces of it, and see that for certain pieces of it, its inverse is also a function. So for example, if I focus primarily on the domain values where x is less than 0, I can look at this piece of the function. So this is represented by f of x equals x squared when x is less than 0. Now, if I were to reflect that across y equal x, what would its reflection look like? It would look like this. So f inverse for this restricted domain is in fact a function. Now, what if I look at this piece? So for this piece, I have f of x equals x squared when x is greater than or equal to 0. If I reflect that piece across the line y equal x, I'm going to get what? Something that looks like this. And its inverse is also a function. So if we restrict the domain of the function to try to find the inverse, we see that each of those pieces does in fact have an inverse. So f of x equals x squared, where x is less than 0, has a inverse, and f of x when x squared equals x squared, where x is greater than or equal to 0, also has an inverse.